If you step far enough back to see an entire spiral galaxy at once, the first thing that strikes you is not chaos, but order. Hundreds of billions of stars moving in disciplined paths, arranged into thin, elegant spiral arms that persist for billions of years. There is no obvious tearing, no explosive disintegration, no sense that the structure is struggling to survive. Just calm, continuous rotation, as steady as a rhythm that began long before Earth even formed. And that calm is the problem. Because when you sit down and write the equations we trust, when you add up the mass of everything we can actually see, stars, gas, dust, and then ask a brutally simple question, the universe gives an uncomfortable answer. If these galaxies are spinning this fast, what is holding them together? According to everything we know from ordinary gravity, the answer should be nothing. Imagine a spinning disk. The farther you move from the center, the weaker the gravitational pull becomes, and the slower objects must move if they want to stay bound. We see this perfectly in the solar system. Mercury races around the Sunday. Neptune crawls. Gravity fades with distance, and motion obediently follows. So when astronomers first began measuring how fast stars orbit inside galaxies, they expected to see the same pattern. Fast motion near the center, gradual slowing toward the edges, a graceful gravitational tapering off. Instead, they found something profoundly unsettling. Stars at the outer edges of galaxies were moving just as fast as stars much closer to the center, not a little faster than expected, not within the margins of error. They were moving far too fast. Fast enough that, if only the visible matter were present, those stars should already be gone, flung outward into intergalactic space long ago. The galaxy, by all rights, should be flying apart. The first instinct was not to invent something invisible. Scientists are conservative creatures. When reality disagrees with expectation, the safest assumption is that something is wrong with the measurement. Maybe dust was hiding mass. Maybe faint stars were being missed. Maybe the distances were wrong. Maybe the instruments were lying. But as telescopes improved, the problem only sharpened. Better detectors, cleaner data, broader wavelength coverage. The story refused to change. The rotation curves, the plot showing how orbital speed changes with distance from the galactic center, were stubbornly flat. This moment matters, not because it introduced a fashionable mystery, but because it forced the universe into a corner. Either gravity itself behaves differently on galactic scales, or there is far more mass present than we can see. There is no third option. The stars are not confused. They are responding to a gravitational field that is very real, very precise, and very much stronger than visible matter alone can produce. What makes this even stranger is how relaxed galaxies appear. There is no sign of dynamic distress, no violent instability, no evidence that they are temporarily balanced on the edge of collapse. Everything moves as if it knows exactly where it belongs, as if there is a deep, invisible structure quietly guiding every orbit. Here is where human intuition tends to betray us. We instinctively assign importance to what shines. Stars feel important because they glow, Nebulae feel significant because they are colourful, but gravity does not care about light. It does not respond to brilliance or darkness. It responds only to mass. And the universe is under no obligation to make its most important ingredients visible to us. If you could somehow erase all the light from a galaxy, leaving only its gravitational fingerprint, the stars would continue to follow the same paths. Light is not what binds them. Something else does. Something extended, massive, and utterly silent. This is not a minor accounting error. Without this additional mass, galaxies are not just slightly unstable, they are catastrophically impossible. They would shear apart in a fraction of the time they have clearly existed. Their thin disks would warp, fragment, and dissolve. Spiral structure would be fleeting, not ancient. And yet, when we look deep into space, when we look back in time, we see spiral galaxies already in place when the universe was young. Stable, ordered, calm. Whatever is holding them together has been there from the beginning. This is not a late fix, not a local anomaly. It is a foundational feature of how cosmic structure forms. A quiet question begins to grow louder. If the universe can be so thoroughly governed by something we cannot see, how much of reality operates beyond our direct perception? There is a subtle reversal here that is easy to miss. Dark matter was not proposed because scientists wanted mystery. It was accepted because the universe was behaving too well, too consistently, too obediently to invisible rules. This is not a story about adding an exotic ingredient to save a beautiful theory. It is a story about motion refusing to lie. Stars do not offer opinions. They do not care what we hope is true. They simply respond to the forces acting upon them, and in doing so, they write an honest record of where mass truly resides. That record says, with remarkable clarity, that most of the mass in a galaxy does not shine. From this point forward, the question stops being a vague "what is dark matter" and becomes something far more concrete. What does this invisible component actually do? How is it arranged? How does it sculpt orbits, stabilize disks, and preserve structure over cosmic time? Because the moment you understand what prevents stars from escaping their galaxies, you begin to understand why the universe is filled with structure at all. Why it is not just a thin, drifting mist of matter fading endlessly into darkness. Once you accept that the stars are telling the truth, the problem deepens very quickly. Because it isn't confined to one strange galaxy or one peculiar measurement. The mismatch between gravity and visible matter appears everywhere you look, and it grows more severe as you zoom out. At first, the discrepancy seems almost manageable. Perhaps galaxies are unusual. Perhaps their light misleads us. But then astronomers began weighing not individual galaxies, but entire groups and clusters of them. Vast cities of galaxies bound together by gravity. These are systems so large that individual stars are irrelevant. What matters is how the galaxies themselves move, how fast they orbit the collective center of mass. And once again, gravity refuses to behave. Galaxies inside clusters move far too quickly to be held together by the mass we can see. If only stars and glowing gas were present, these clusters should disperse, They're galaxies drifting apart over cosmic time. But they don't. They remain bound, stable, on timescales measured in billions of years. The numbers are brutal. In some clusters, more than 80% of the mass appears to be missing, not hidden behind dust, not locked up in faint stars, simply absent from the luminous universe altogether. At this scale, excuses run out. You cannot plausibly hide that much ordinary matter without it betraying itself. Gas that dense would glow in X-rays. Stars that numerous would leave fingerprints in starlight. Black holes of that abundance would distort space in unmistakable ways. Yet none of these signatures appear in sufficient quantity. What remains is not ignorance of what we are seeing, but a confrontation with what we are not. This is where the temptation to abandon gravity itself becomes strong. Perhaps Newton's law, or even Einstein's refinements of it, fail on galactic scales. Perhaps the force weakens or strengthens in subtle ways over vast distances. This idea is not foolish. It has been explored carefully and seriously for decades. But modified gravity has a problem. Actually, several. The first is consistency. Any change to gravity that explains galaxy rotation must also explain clusters, gravitational lensing. The growth of large-scale structure and the precise patterns seen in the cosmic background radiation left over from the early universe. Fixing one scale while breaking 5 others is not a solution. It is an evasion. The second problem is shape. The gravitational pull inferred from observations is not arranged like stars or gas. It forms enormous, roughly spherical halos around galaxies, extending far beyond their visible edges. The pull does not track light. It does not care where stars are densest. It behaves as if most of the mass lives in a vast, diffuse envelope that stars merely inhabit. Gravity modified or not, something with this spatial distribution must exist. Then comes the most damning evidence of all, gravity acting where ordinary matter has clearly moved away. When massive cosmic structures collide, clusters crashing through one another at millions of kilometers per hour, their components behave very differently. Stars pass through almost unaffected, like distant insects in a swarm. Gas clouds slam together, heat up, slow down, and glow fiercely in X-rays. This separation allows astronomers to map where ordinary matter ends up after the collision. And yet, when the gravitational field of the system is reconstructed, it does not follow the gas. It follows something else, something collisionless, something that passed straight through without slowing down. If gravity were simply misbehaving, it would still point toward the visible mass. But it doesn't. It points somewhere else entirely. At this point, the phrase missing mass becomes misleading. Nothing is missing. The mass is there, exerting gravity with perfect consistency. It simply does not interact with light, heat, or electromagnetic forces in any appreciable way. It does not shine, absorb, reflect, or radiate. It participates only in gravity, and perhaps in interactions we have not yet learned to detect. This realization changes the nature of the problem. We are no longer asking why galaxies rotate too fast. We are asking why the universe appears to be built on an invisible gravitational framework, with luminous matter acting almost like decorative trim. And this framework is not subtle. It dominates. In a typical galaxy, the stars and gas, you see, account for only a small fraction of the total mass. The rest resides in this unseen component, outweighing the visible by a factor of 5 or more. In clusters, the imbalance is even more extreme. This is where the idea of a dark halo becomes unavoidable, not as a speculative add-on, but as a structural requirement. Without it, nothing works. With it, everything suddenly falls into place. Not just galaxy rotation, but cluster dynamics, lensing patterns, and the large-scale architecture of the universe. There is a quiet elegance to this. The equations do not become messy. They become simpler. Galaxies behave the way they do because they are embedded inside something much larger than themselves. Their stars are not free agents. They are tracers, moving through a gravitational landscape they did not create. This also explains something that had long been puzzling: why galaxies of wildly different sizes and brightnesses show surprisingly similar rotation behavior. If stars dominated the mass, every galaxy would be dynamically unique. But if most of the mass comes from an extended, invisible halo, then galaxies inherit a kind of structural uniformity. Their individuality is painted in light, but their bones are dark. And once you see this, you begin to notice its implications everywhere. The visible universe becomes less like a self-supporting structure and more like frost forming on a window. Beautiful, intricate, but dependent on an underlying surface you cannot see. The unsettling thought is not just that most matter is invisible. It is that everything we normally associate with substance, light, heat, chemistry, life, is riding on top of something far more massive and far more indifferent. Gravity, it turns out, is not failing us. It is doing exactly what it should. The failure lies in assuming that the luminous universe is the whole universe. Once that assumption is dropped, the cosmos stops looking broken and starts looking profoundly asymmetric. A place where what shines is rare, what binds is hidden, and what truly governs motion does so without ever announcing its presence. And if this invisible mass controls galaxies and clusters so completely, then the next question becomes unavoidable. How early did it take charge? Did it merely stabilize structures after they formed, or was it there first, laying down the gravitational scaffolding before the first stars ever ignited? Because if dark matter shaped gravity from the very beginning, then galaxies are not just collections of stars. They are visible expressions of an invisible architecture that decided, long before light existed, where matter would be allowed to gather at all. The moment you stop thinking of dark matter as a mysterious substance and start thinking of it as a structure, everything changes. Because what observations are really telling us is not just that extra mass exists, but that it exists in a very specific arrangement, not clumped like stars, not flattened like disks, but spread out into enormous, roughly spherical envelopes that swallow galaxies whole. These are dark matter halos, and they are not decorative. They are load-bearing. Every spiral galaxy you see is embedded inside one, the glowing disk, with all its stars, gas, dust, planets, and life is a thin, fragile layer floating deep inside a gravitational ocean that extends far beyond anything we can see. The halo does not end at the last spiral arm. It does not fade where the light fades. It continues outward, tens or hundreds of thousands of light years into space, dominating the galaxy's mass budget almost entirely. From a dynamical perspective, the stars are not the main event. They are test particles. This is why rotation curves flatten. As you move outward through a galaxy, the amount of dark matter enclosed within your orbit keeps increasing. Even though the visible mass drops off, the gravitational pull does not weaken the way it should. The halo quietly takes over. By the time you reach the outskirts of a galaxy, most of the gravity you feel comes from matter that emits no light at all. This realization forces a deep shift in how we imagine galaxies. We tend to picture them as collections of stars that somehow gathered together and then stabilized. But in reality, the sequence is reversed. The dark matter halo comes first. It collapses under its own gravity early in the universe's history, forming a vast gravitational well. Ordinary matter, gas made of protons, electrons, and atoms, falls into that well later, cooling, condensing, and eventually igniting into stars. Galaxies are not self-made, they are guests. The halo defines the gravitational rules of the system. It sets the orbital speeds. It controls how tightly stars can be bound. It determines how the galaxy responds to disturbances. Without it, the luminous disk would be dynamically fragile, easily warped, or torn apart by even modest gravitational encounters. This becomes especially clear when you think about stability. A rotating disk of stars is an inherently delicate structure. Left to itself, it is prone to instabilities that amplify small disturbances into large-scale chaos. Bars form, spirals over-tighten, orbits cross, energy is redistributed violently. Over time, the disk thickens, heats up, and loses its graceful form. And yet, spiral galaxies remain thin and ordered for billions of years. The halo acts as a stabilizing anchor. Its massive, roughly spherical gravity field smooths out irregularities. It absorbs angular momentum. It dampens the growth of instabilities that would otherwise shred the disk. In effect, it provides a deep gravitational cushion that allows delicate luminous structures to survive in a universe that is anything but gentle. This also explains why galaxies can be so different in appearance, yet so similar in behavior. Two galaxies may have vastly different numbers of stars, different colors, different histories of star formation. But if their dark matter halos are similar, their overall dynamics will be strikingly alike. The visible differences are surface details. The underlying gravitational architecture is what matters. Once you accept this, the role of dark matter stops feeling exotic and starts feeling inevitable. Any long-lived, rotating structure in a universe governed by gravity needs a stabilizing mass distribution. Ordinary matter cannot provide it alone. It dissipates energy. It cools, it collapses, it radiates. Dark matter does none of these things. It stays extended, diffuse, dynamically cold in the sense that it moves primarily under gravity, not pressure or radiation. It is, in a very literal sense, the perfect scaffolding, and the stars know it. You can see this in the motions of stellar populations within galaxies. Young stars, old stars, globular clusters, satellite galaxies, all trace the same underlying gravitational field. They move as if embedded in something much larger than the luminous disk. Their orbits curve, precess, and oscillate in ways that only make sense if a massive, invisible halo surrounds them. Even the shape of a galaxy's halo matters. Slight deviations from perfect sphericity leave subtle fingerprints in stellar motions. By studying these motions carefully, astronomers can infer not just the presence of dark matter, but its distribution, its concentration, and its overall geometry. All of this from objects that cannot see it. There is a quiet irony here. The most dominant component of galaxies does not announce itself with light or heat. It reveals itself only through patience, through careful tracking of motion, through the willingness to trust gravity over intuition. And gravity is very clear about this. The visible galaxy is not the true boundary of the system. It is a luminous island inside a much larger, darker continent. This changes how we think about galactic identity. Where does a galaxy end? At the last star, at the last detectable gas cloud, or at the edge of its dark matter halo, where its gravitational influence finally yields to the cosmic background? From a dynamical perspective, the answer is unambiguous. The halo is the galaxy. The stars are simply the parts we can see. This perspective also dissolves an old misconception that dark matter is something added to galaxies to fix a problem. In reality, galaxies are what get added to dark matter halos. The halos are the primary structures. The luminous components are secondary, contingent, and comparatively minor. Once you internalize that, a deeper pattern begins to emerge. The universe does not build structures from the top down, starting with bright, complex objects. It builds them from the bottom up, starting with invisible gravitational wells that quietly dictate where complexity is allowed to arise. And this brings us to an unavoidable realization. If dark matter halos define the structure and stability of galaxies today, then they must have been even more important in the past, when the universe was hotter, denser, and more chaotic. They must have shaped not just how galaxies move, but how they formed in the first place. Which means the next question is no longer about present-day motion. It is about cosmic memory, about whether galaxies are merely collections of stars, or whether they are fossils, visible traces of an invisible architecture laid down long before the first light ever shone. Because if dark matter halos existed before stars, then every galaxy is, at its core, a monument to something we have never seen, only felt, guiding matter into form long before the universe learned how to glow. A rotating disk of stars looks serene, but dynamically it is a precarious thing. Strip away the poetry, and what you have is an enormous collection of masses moving on near circular orbits, each one tugging on the others, each one vulnerable to even the slightest imbalance. Left on its own, a disk like this should not age gracefully. It should distort, overheat, and ultimately destroy the very order that makes it recognizable as a spiral galaxy. This is not speculation. It is what the equations say. In a disk dominated only by its visible matter, small irregularities grow instead of fading away. A tiny overdensity pulls in nearby stars, which deepens the gravitational well, which pulls in more stars. The process feeds on itself. Spirals tighten. Bars grow stronger. Orbits become elongated and chaotic. Energy is shuffled around, heating the disk and puffing it up until the thin, elegant structure is gone. In other words, spiral galaxies should be short-lived, and yet they aren't. We see thin, stellar disks that have survived for billions of years. We see delicate spiral arms that reform again and again without tearing the system apart. We see ordered rotation persisting across cosmic time, even in environments where gravitational harassment from neighboring galaxies should have been catastrophic. Something is absorbing the chaos. The dark matter halo changes the game entirely. By surrounding the luminous disk with a deep, massive gravitational field, it fundamentally alters how instabilities behave. The disk is no longer the sole source of gravity. It is no longer forced to support itself. Instead, it is embedded in a far larger potential that dominates the dynamics. When a perturbation arises in the disk, the halo acts like a shock absorber. It soaks up angular momentum. It spreads out gravitational stresses. It prevents local disturbances from snowballing into global destruction. The disk can flex without snapping. This is why bars do not instantly consume galaxies. This is why spiral arms can be long-lived patterns rather than runaway catastrophes. This is why disks remain thin instead of heating themselves into featureless blobs. The halo does not eliminate instability. It regulates it. This regulation is subtle but decisive. Spiral arms, for example, are not rigid structures made of fixed stars. They are density waves, regions where stars bunch up temporarily before moving on. Without a stabilizing halo, these waves would rapidly steepen and collapse. With one, they can persist, reform, and dissipate in a controlled way, like ripples on the surface of a deep lake rather than breakers on a shallow shore. The same is true for bars. Bars redistribute angular momentum, funneling gas toward galactic centers and triggering star formation. In a halo-free galaxy, this process would run to completion, leaving behind a hot, spheroidal remnant. In a halo-dominated system, the bar transfers much of its angular momentum to the dark matter itself. The halo quietly accepts it, allowing the disk to survive the event. This is one of the most counterintuitive aspects of dark matter's role. It does not merely hold stars in place. It actively participates in the galaxy's dynamical life, exchanging energy and momentum without ever lighting up or announcing itself. And the effect scales with mass. The more dominant the halo, the more stable the disk. This explains why low-mass galaxies are often messy, irregular, and easily disturbed. Their halos are smaller less capable of damping instabilities. High-mass spiral galaxies, wrapped in enormous halos, can maintain their structure against both internal chaos and external threats, even warps. The gentle bending of galactic disks tell this story. Many spiral galaxies are warped at their edges, as if slightly twisted. These warps are not signs of imminent destruction. They are slow responses to gravitational torques, often from misaligned halos or interactions with surrounding matter. Without a massive halo, such distortions would tear disks apart. With one, they remain mild, controlled, and long-lived. There is a profound implication here. The most fragile-looking structures in the universe owe their survival to the most invisible component. The elegance of spiral galaxies is not a triumph of luminous matter arranging itself beautifully. It is a side effect of being cradled inside something much larger and much more forgiving. This also reframes the idea of galactic maturity. A stable disk is not merely old, it is well supported. Its history is written not just in its stars, but in the mass and shape of its halo. Galaxies with similar stellar populations, but different halo properties, evolve in radically different ways. One remains thin and ordered. The other heats up, thickens, and loses its identity. So when we look at a galaxy and admire its symmetry, we are really admiring the success of an invisible balancing act. There is another quiet consequence of this stabilizing role. It sets limits. Not every configuration of stars is allowed. Without dark matter, disks could not grow large without self-destructing. With too little halo mass, they cannot remain thin. With too much concentration, they become overly rigid, suppressing the very instabilities that drive star formation and renewal. Dark matter does not just prevent chaos, it defines the narrow corridor between rigidity and ruin. This corridor is where familiar galaxies live. And once again, this pushes against a comforting intuition. We like to imagine that stars control their own destiny, that galaxies are self-organizing systems shaped primarily by what we can see. But the evidence points elsewhere. The luminous disk is more like a dancer moving across a stage whose shape, slope, and elasticity were set long before the performance began. Change the stage, and the dance changes. This perspective also explains why simulations without dark matter fail so spectacularly. When you try to build galaxies from ordinary matter alone, disks either never form properly or disintegrate almost immediately. Add a dark matter halo, and suddenly the same physics produces structures that look eerily like the real universe. Not because the simulation was forced to behave, but because it was finally given the missing support. At this point, the conclusion becomes difficult to avoid. Dark matter is not a passive background ingredient. It is an active regulator of motion, stability, and survival. It allows complexity to exist without tearing itself apart. And this raises a deeper question, one that shifts our attention away from present-day galaxies and toward their origins. If dark matter is responsible for keeping disks intact, then it must also have influenced which disks formed in the first place. It must have decided where order was even possible amid the chaos of the early universe. Because stability is not something you add later. It has to be built in from the start. And if dark matter wrote those rules early on, then galaxies are not just beautiful accidents. They are the long-term consequences of an invisible framework that has been quietly governing structure since before the first stars ever learned how to shine. A galaxy is not just a snapshot. It is a memory. Every star inside it carries information about the gravitational environment in which it was born and evolved. Its orbit is not random. Its speed, its tilt, its eccentricity, all of these are responses to a gravitational field that has been acting for billions of years. And when you look closely enough, those orbits tell a story that light alone never could. In a universe made only of ordinary matter, stellar orbits would be chaotic historians. Close encounters would scatter stars, erase coherent motion, and gradually wipe out any trace of the galaxy's past. Over time, everything would blur toward equilibrium. Structure would forget itself. But real galaxies remember. They remember how gas first fell inward. They remember mergers long after the visible scars have faded. They remember whether their growth was gentle or violent. And the reason they can remember is because dark matter preserves that memory. Consider the difference between circular and eccentric orbits. In a well-ordered disk, most stars move on nearly circular paths, confined to a thin plane. This is not a trivial condition. Circular orbits are fragile. They are easily disrupted by gravitational kicks, by fluctuations in mass, by encounters with other stars or passing galaxies. Without a dominant halo, these orbits would rapidly degrade. Stars would gain random motions. The disk would thicken. Order would dissolve into heat. Yet in spiral galaxies, even very old stars often remain on surprisingly regular orbits. Their motions still reflect the original angular momentum of the gas cloud from which they formed. This persistence is a clue. It tells us that the gravitational environment has been remarkably steady over cosmic time. That steadiness comes from the halo. Dark matter does not cool, collapse, or fragment the way ordinary matter does. It does not clump into dense knots that violently scatter passing stars. Instead, it forms a smooth, slowly evolving gravitational background. Stars move within it like leaves drifting through a deep, slow-moving current rather than bouncing through a crowded room. This smoothness matters enormously. It means that stars can orbit for billions of years without having their paths randomized. The galaxy retains a kind of dynamical coherence, a long-term memory encoded in motion. You see this most clearly when you compare different stellar populations. Young stars, born recently from cold gas, move in thin, orderly disks. Older stars have slightly puffier distributions and higher random velocities, reflecting a history of gradual heating. But the transition is gentle. It is cumulative. It unfolds over billions of years, not catastrophically in a few orbital periods. That gradualism is a signature of a halo-dominated system. In a purely baryonic galaxy, violent relaxation would dominate. Early instabilities would erase initial conditions quickly. The system would forget how it formed, but real galaxies do not forget so easily. Their stellar kinematics preserve a fossil record of their assembly. Even satellite galaxies tell this story. Small galaxies orbiting a larger host follow paths that trace the host's extended dark matter halo, not just its luminous disk. Their motions reveal the halo's mass, shape, and reach. Some are slowly spiraling inward, their orbits decaying as energy is transferred to the dark matter itself. Others remain on stable paths for billions of years. Again, the halo is not passive. It absorbs energy. It reshapes trajectories. It mediates interactions without tearing the system apart. This is especially important during mergers. When galaxies collide, the event is anything but gentle. Orbits are scrambled. Gas clouds shock and radiate. Stars are flung onto new paths. It is tempting to imagine that such events would completely erase a galaxy's past. But even here, memory survives. After a merger, stars settle into new configurations that still reflect the combined dark matter halos of the original galaxies. The final system's kinematics encode information about the mass ratios, impact parameters, and orbital geometries of the collision. Astronomers can read this information long after the visible chaos has faded. This would be impossible without dark matter, without a dominant, collisionless component to absorb energy and smooth the gravitational potential. Mergers would be far more destructive. They would leave behind systems with little coherent motion, little structure, and little trace of their origins. Instead, galaxies emerge from these encounters, transformed but not erased. They remember. There is a deeper implication here. Dark matter does not merely stabilize galaxies in a static sense. It stabilizes their histories. It allows structure to evolve without being constantly reset. It creates a universe where the past matters. This has consequences for how we interpret what we see. When astronomers map stellar motions today, they are not just measuring present-day dynamics. They are reconstructing a timeline, the velocity dispersion of stars, the tilt of their orbits, the presence of coherent streams. All of these are echoes of earlier gravitational events, preserved by the halo's steady hand. In this sense, dark matter acts like a low-noise recording medium. It does not overwrite information quickly. It allows subtle patterns to persist. And because of that, galaxies become readable. This also explains why certain galactic features are so long-lived. Thick disks, stellar halos, globular cluster systems, these are not transient accidents. They are durable components whose properties depend sensitively on the mass and shape of the dark matter halo. Change the halo, and the entire dynamical narrative changes with it. Even the very concept of a quiet galaxy depends on this. A galaxy can experience minor mergers, tidal interactions, and internal instabilities without losing its identity, because the halo buffers these events. It spreads their effects over time, preventing sharp disruptions from becoming existential threats. This buffering is what allows complexity to accumulate rather than constantly reset. And here, the story circles back to something subtle but profound. We often think of structure as something built from visible pieces. Stars assembling into galaxies, galaxies assembling into clusters. But the true continuity, the thread that connects past to present, is gravitational, and that thread is woven primarily by dark matter. Without it, galaxies would be amnesiacs. Each violent episode would wipe the slate clean. With it, they become archives. So, when we look at the orderly rotation of a disk, or the graceful motion of a stellar stream, we are not just seeing physics in action, we are seeing memory preserved by invisibility. This realization shifts the focus once again. If dark matter preserves the dynamical memory of galaxies, then it must also preserve the memory of something even earlier, of the initial conditions of the universe itself. The tiny density fluctuations present shortly after the Big Bang must still echo through today's structures, amplified but not erased, which means galaxies are not just memories of their own lives. They are memories of the universe's childhood, written into motion by an invisible hand that never needed light to leave its mark. And that raises the next question naturally, almost inevitably. If dark matter preserves memory so effectively, then how far back does that memory go? Does it reach all the way to the earliest moments when structure first began to form, when the universe was still smooth, hot, and almost featureless? Because if it does, then dark matter is not just shaping galaxies. It is carrying the universe's origin story forward, one orbit at a time. When galaxies collide, nothing behaves the way intuition expects. There are no fireballs swallowing entire star systems, no widespread stellar crashes. Stars are too small and too far apart for that. They pass through one another like ghosts, barely noticing the encounter. Gas behaves very differently, slamming together, compressing, heating, lighting up in shock fronts that can be seen across the universe. But the most important component, the one that determines the outcome, does something stranger still. It passes straight through. On cosmic scales, galaxy mergers are not collisions in the everyday sense. They are gravitational interpenetrations. Two vast systems approach, overlap, and then slowly disentangle, reshaping each other through tidal forces rather than impact. And at the heart of this process is dark matter, behaving in a way that reveals its true nature with almost brutal clarity. When two galaxies begin to merge, their dark matter halos meet first. Long before the luminous disks touch, the invisible envelopes overlap, distort, and begin exchanging energy. This interaction dominates the event. The stars and gas are passengers, responding to a gravitational choreography already underway. Dark matter does not collide. It does not shock. It does not heat up. It simply continues on, guided only by gravity. This makes it effectively collisionless. And that single property explains an enormous amount about how galaxies evolve. As the halos interpenetrate, they pass through one another, slowing only through gravitational interactions, not friction. In the process, they absorb orbital energy and angular momentum from the merging system. This is where much of the violence goes. The chaos is not erased. It is redistributed into the dark sector. The visible matter tells a different story. Gas clouds collide head-on. They lose energy rapidly, radiating it away as heat and light. This causes gas to sink toward the center of the merging system, often triggering bursts of star formation or feeding central black holes. Stars, unaffected by collisions, are flung onto elongated orbits, forming tidal tails and stellar streams that arc gracefully through space. But none of this determines whether the final system remains bound. That decision belongs to the dark matter halos. Because they carry most of the mass, the halos determine whether the merger results in a single galaxy or a dispersal. They decide how tightly the remnants are held together, how quickly the system settles, and what kind of galaxy emerges at the end. Without halos, mergers would be catastrophic, producing hot, diffuse remnants with little coherent structure. With halos, something remarkable happens. Order re-emerges. This becomes strikingly clear in systems where the separation between components can be observed directly. In some merging galaxy clusters, the gas has been stripped and slowed, glowing brightly in X-rays at the collision site. The galaxies themselves have moved ahead, and the gravitational field, mapped through gravitational lensing, follows neither the gas nor the stars. It follows the dark matter. The gravitational pull peaks where there is almost no visible matter at all. The mass has passed through the collision unimpeded, leaving the luminous debris behind. This is not a subtle effect. It is a clean separation between what shines and what weighs. At this point, explanations that rely solely on modified gravity break down completely. If gravity were simply behaving differently, it would still point toward the visible mass. But it doesn't. It points towards something else, something invisible, something collisionless. Dark matter is not just inferred here, it is exposed by contrast. And this behavior has long-term consequences. During mergers, dark matter halos act as reservoirs that soak up energy, allowing the system to relax rather than fly apart. This process, known as dynamical friction, slows orbiting galaxies and causes them to spiral inward over time. The friction does not come from collisions, but from gravitational wakes stirred up in the dark matter itself. In effect, the halo responds to motion by reshaping its own gravitational field, pulling back on the intruder. The intruder loses energy, the halo gains it, and the merger proceeds toward completion. This mechanism is essential for building large galaxies. Without it, small galaxies would orbit forever without merging. Structure would remain fragmented. The universe would look radically different. Instead, halos enable a hierarchy. Small systems fall into larger ones. Larger systems grow even larger. The cosmic landscape evolves through a sequence of mergers mediated almost entirely by invisible matter. And importantly, this process is gentle in a cosmic sense. It does not instantly erase structure. It allows remnants to settle into new equilibria. Disks may be destroyed or thickened. Ellipticals may form, but the system remains bound, coherent, and long-lived. This is why galaxy mergers do not mark the end of structure, but a transformation of it. There is a subtle but powerful point hidden here. Dark matter allows galaxies to interact without annihilating one another. It permits change without dissolution. It enables violence without total loss of identity. In a universe without dark matter, mergers would be terminal events. With it, they are chapters. This also explains why merger histories can be reconstructed. Stellar streams, shell structures, and kinematic subcomponents persist long after the visible chaos fades. These features are preserved because the halo provides a smooth gravitational backdrop in which debris can orbit for billions of years without being erased. Once again, dark matter preserves memory. And the deeper implication is this: the large-scale structure of the universe is built not through contact, but through passage, through systems moving through one another, exchanging energy gravitationally, reshaping themselves without ever truly colliding. This is an alien way of building complexity. It has no analogue in everyday experience. And yet, it is the dominant mode of cosmic evolution. The universe grows not by smashing things together, but by letting invisible mass guide encounters towards stable outcomes. Seen this way, dark matter is not just a stabilizer or a scaffold. It is a mediator. It governs how structures interact, how they merge, and how they survive those encounters. And this inevitably leads to another shift in perspective. If dark matter halos control mergers, then they also control where matter ends up after those mergers. They decide which stars are retained, which are flung into intergalactic space, and where new structures can form. Which means the visible arrangement of galaxies we see today, their shapes, environments, and histories, is not just the result of luminous matter behaving under gravity. It is the outcome of countless interactions choreographed by something that never once revealed itself directly. And that realization forces the next question into view. If dark matter governs mergers and interactions, then it must also govern the very geography of the universe. The locations where galaxies cluster, the filaments they trace, the voids they avoid. Because if invisible mass decides how galaxies meet, then it must also decide where they are allowed to be. And that takes us beyond individual galaxies, beyond collisions, and into the vast cosmic web itself, where dark matter's role is no longer subtle, but architectural, where stars are allowed to exist is not a poetic question. It is a brutally physical one. In the early universe, ordinary matter was everywhere, hot, diffuse, and restless. Hydrogen and helium filled space almost uniformly, expanding, cooling, trying to follow gravity inward while radiation pressure pushed back. Left to itself, this matter struggled to settle. It could not easily decide where to gather, where to stay, or where to ignite. And yet, galaxies formed, not everywhere, not uniformly, only in specific places, with specific masses, at specific times. The universe did not light up randomly. It followed a map. That map was drawn by dark matter. Long before the first star existed, dark matter had already begun to clump. While ordinary matter was still tightly coupled to radiation, prevented from collapsing by intense pressure, dark matter felt only gravity, It began to form small overdensities, tiny regions where mass was slightly higher than average. Over time, gravity amplified those differences. Small clumps grew. Clumps merged. A hidden landscape of gravitational wells emerged. This happened quietly, invisibly, and decisively. When the universe finally cooled enough for ordinary matter to decouple from radiation, it did not collapse everywhere. It flowed. It streamed. It fell preferentially into the gravitational wells that were already there. Dark matter did not just help galaxies form. It told baryonic matter, where galaxy formation was even possible, no halo, no galaxy. This is not a metaphor. It is a threshold condition. Below a certain dark matter halo mass, gas simply cannot remain bound. Radiation from the first stars, from the cosmic background, from reionization itself, heats the gas and blows it back into intergalactic space. Star formation is shut down before it can begin. The universe becomes selective. Only halos massive enough to hold on to gas against this heating are allowed to host stars. This immediately explains something that once seemed mysterious: why there are so many dark halos with little or no visible matter. The universe is full of potential galaxies that never quite made it. Their dark matter halos exist, but they never cross the threshold required to light up. They are gravitational structures without luminous expression, and this selectivity continues even within galaxies. Gas does not turn into stars simply because it is present. It must cool. It must lose energy. It must settle into dense regions where gravity can overcome internal pressure. Dark matter controls all of this indirectly by shaping the gravitational potential in which gas moves. In a shallow halo, gas heats easily and escapes. In a deep halo, gas is confined, compressed, and allowed to cool efficiently. But even here, there are limits. In extremely massive halos, those corresponding to galaxy clusters, gas can become so hot that cooling is inefficient. Star formation is suppressed again. There is a narrow window. Dark matter defines that window. It decides which halos are too small to hold gas, which are just right for sustained star formation, and which are so massive that gas stagnates in a hot, diffuse state. The visible universe occupies a surprisingly thin slice of the total mass spectrum, permitted by invisible constraints. This is why galaxies have characteristic masses. This is why star formation peaks at certain epochs and declines afterward. This is why the universe does not fill itself uniformly with stars. Dark matter is not just scaffolding. It is a gatekeeper. Even the spatial distribution of stars within galaxies reflects this control. Stars form where gas can sink deepest into the gravitational potential, typically near the center of the halo or within dense substructures shaped by it. The halo sets the overall geometry within which disks, bulges, and stellar halos emerge. Change the halo, and you change where stars are allowed to exist. This also explains why galaxies with similar stellar masses can behave very differently. Two galaxies may contain the same number of stars, but if their dark matter halos differ in concentration or shape, their star formation histories diverge. One may sustain star formation for billions of years. The other may shut down early, becoming red, quiet, and inert. The stars do not make that decision. The halo does. And this influence extends beyond individual galaxies into their environments. In dense regions of the universe, where halos are massive and closely packed, galaxies tend to lose their gas. Tidal forces, ram pressure stripping, and gravitational harassment, all mediated by the underlying dark matter distribution, quench star formation. In quieter regions, smaller halos can retain gas longer, forming stars more gradually. The cosmic ecology is set by invisible terrain. Once you see this, the luminous universe starts to look less like a primary structure and more like a byproduct. Stars are not the default outcome of matter. They are a conditional one. They appear only where dark matter permits them to. This flips a deeply ingrained intuition. We tend to think of dark matter as something added to galaxies, something invoked to explain odd motions after the fact. In reality, ordinary matter is the latecomer. It is the guest responding to rules that were already written, and those rules are unforgiving. Gas that falls into a halo that is too small will be lost. Gas that falls into a halo that is too large may never cool. Gas that falls into the right halo, at the right time, under the right conditions, can ignite stars and build complexity. The universe is not democratic. It is selective. This selectivity also explains why structure formation proceeds unevenly across time. Star formation rises, peaks, and then declines, not because the universe runs out of gas, but because dark matter halos evolve. As halos grow and merge, they cross thresholds that change how gas behaves. Cooling shuts down. Feedback becomes more effective. The conditions that once favoured star birth disappear. The night sky we see today is the afterimage of those conditions, frozen into place. There is something almost unsettling about this. Everything we associate with richness, stars, planets, chemistry, life, exists only in regions where an invisible substance arranged gravity just so, not too weak, not too strong, not too chaotic, not too rigid. Dark matter does not care about stars. It does not respond to light or heat or nuclear fusion. And yet, without intending to, it decides where all of those things can happen. It is not a creator in any conscious sense. It is an enforcer of constraints. And constraints, in physics, are destiny. Once you accept that dark matter determines where stars are allowed to exist, another implication follows naturally. If it controls the placement of stars, then it controls the placement of galaxies themselves. Not just whether they form, but where they gather, how they align, and how they trace the large-scale structure of the universe. Which means the glowing patterns we see across billions of light years, the filaments, the clusters, the vast, empty voids, are not drawn by light at all. They are traced by it. Because the next scale up, the largest structure of all, is where dark matter stops whispering and starts shouting, where it becomes the skeleton of the cosmos itself. If you pull back far enough, far beyond individual galaxies, far beyond clusters, the universe stops looking like a collection of objects and starts looking like a pattern. Not a smooth fog of matter, not a random scatter of lights, but an intricate network, long filaments stretching across hundreds of millions of light years, intersecting at dense nodes, surrounding vast, nearly empty voids. This is the cosmic web, and it is not traced out by stars. It is traced out by gravity, acting on something that does not shine. The largest structures in the universe were never built from the bottom up by galaxies assembling themselves through chance encounters. They were built from the top down by dark matter collapsing into a vast skeletal framework, long before the first galaxy ever formed. Ordinary matter did not decide where to go. It followed. In the earliest moments after the Big Bang, the universe was astonishingly smooth. Density variations were tiny, differences of 1 part in 100,000. Left to ordinary matter alone, these ripples would have taken far too long to grow. Pressure from radiation would have smeared them out. Gravity would have struggled to gain a foothold. But dark matter felt no such pressure. It began clumping almost immediately, responding only to gravity. Tiny overdensities grew slowly at first, then faster still. Regions slightly denser than average pulled in more dark matter, deepening their gravitational wells. Regions slightly emptier became emptier still. Contrast sharpened. Structure emerged. By the time ordinary matter was free to fall, the map was already drawn. Gas streamed along invisible gradients, flowing down the slopes of the dark matter landscape. It collected where filaments intersected. It avoided the voids, not because it was repelled, but because there was nothing there to pull it in. The web dictated motion on the largest scales imaginable. This is why galaxies are not scattered randomly through space. They line up along filaments like beads on cosmic strings. Clusters form at nodes where filaments meet. Vast regions remain almost empty, not because matter vanished, but because it was never invited in. The luminous universe is an afterimage of this invisible structure. What makes this especially striking is how faithfully galaxies trace the dark matter beneath them. When astronomers map the distribution of galaxies across the sky, they are effectively mapping the underlying dark matter web. The stars merely highlight it, like frost outlining the grain of wood, and the correspondence is not approximate. It is precise. Computer simulations that include dark matter reproduce this web with uncanny accuracy. Filaments, nodes, voids, all emerge naturally when dark matter is allowed to evolve under gravity. Remove dark matter, and the universe fails to build anything resembling what we observe. Structure remains weak, late, and insufficient. The web itself becomes evidence. There is something deeply counterintuitive here. On the largest scales, the universe is not shaped by forces we interact with daily, not electromagnetism, not chemistry, not radiation. Gravity alone rules, and it rules primarily through matter we cannot see. Light is a tracer, not a driver. This means that when we look at the universe's grandest architecture, we are not seeing the structure itself. We are seeing its illuminated edges. The true form is hidden, inferred only through motion, lensing, and the way galaxies arrange themselves like iron filings around an unseen magnet. The cosmic web is also a fossil record. Its structure preserves information about the earliest moments of the universe, the size of voids, the thickness of filaments, the spacing of clusters, all encode the spectrum of primordial fluctuations present shortly after the Big Bang. Dark matter did not erase that information. It amplified it, carrying it forward across cosmic time. Once again, dark matter preserves memory. And because it does so on such enormous scales, it links the smallest galaxies to the universe's infancy. A star orbiting in a quiet spiral arm is, in a very real sense, connected to density ripples imprinted when the universe was less than 1 million years old. The connection is gravitational, continuous, and invisible. This is not poetry. It is causal. The shape of the cosmic web also governs how galaxies evolve after they form. Galaxies do not live in isolation. They flow along filaments, falling toward nodes, accreting matter as they go. Their merger histories, gas supplies, and star formation rates all depend on where they sit within this web. A galaxy embedded deep in a filament experiences a very different life than one near a void. One is fed continuously by inflowing gas. The other starves slowly. One grows through repeated mergers. The other evolves quietly, almost forgotten by the cosmic flow. These differences are not random. They are consequences of position within an invisible structure. Even the largest voids, the great empty bubbles of the universe, are not accidents. They are the natural outcome of dark matter evacuating regions where density was initially slightly lower. Gravity pushed matter out, not in. Over billions of years, emptiness grew. The voids expanded, becoming some of the most pristine regions in existence. And yet, even these voids are shaped by dark matter. Their boundaries are sharp. Their sizes are predictable. Their evolution matches simulations with eerie precision. Nothing about this architecture requires stars. It would exist even if the universe had never learned how to shine. That may be the most unsettling realization of all. The grand design we admire, the filaments stretching across space, the clusters blazing with galaxies, the vast emptiness in between, would still be there in a universe completely devoid of light. It would be invisible, but intact. Gravity would still have done its work. Seen this way, the luminous universe is almost incidental, a late, delicate embellishment painted onto a structure that was already finished. And that perspective forces a quiet humility. We are used to thinking that what we see defines reality. But on the largest scales, reality is defined by what we cannot see, and light merely reveals its outline. The cosmic web is not built from galaxies. Galaxies are built into the web. And once you accept that, another implication follows naturally. If dark matter defines the universe's architecture on the largest scales, then it also governs how structure grows over time. The universe does not assemble randomly. It builds hierarchically, following pathways laid down by the web itself. Which means the next step in the story is not about space, but about time, about how small structures form first, how they merge, how complexity accumulates step by step rather than all at once. Because dark matter does not just shape where things are, it shapes the order in which they come into being. The universe does not build everything at once. It cannot. Gravity is too slow, expansion too relentless, matter too sparse for instant grandeur. Instead, structure emerges the only way it can, incrementally, unevenly, remembering every step along the way. This is known as bottom-up formation, and it is one of dark matter's most consequential legacies. The smallest dark matter halos form first. In the early universe, tiny overdensities collapse, creating gravitational wells with masses far smaller than today's galaxies. These early halos are crude, faint, and short-lived. Many never form stars at all, but they matter because they are the seeds. Over time, gravity pulls these small halos together. They merge. They accrete. They grow. Larger halos are built from smaller ones, not by chance, but by following the pathways defined by the cosmic web. Filaments act like funnels, guiding matter inward. Nodes grow heavier. Hierarchy emerges. This is not speculation. It is written into the statistics of the universe. The distribution of galaxy masses, the abundance of clusters, the frequency of mergers, all match the predictions of a universe dominated by cold, collisionless dark matter assembling from the bottom up. Change the rules, remove dark matter, and the entire timeline collapses. In a universe made only of ordinary matter, structure formation is delayed and inefficient. Pressure smooths out density fluctuations. Collapse happens too late. Galaxies form sluggishly, if at all. By the time anything interesting appears, the universe has already expanded too much to support rich structure. Our universe did not choose that path. Dark matter gave gravity a head start. Because dark matter began clumping early, it allowed structure to grow rapidly while the universe was still dense enough to cooperate. Small halos formed first, then larger ones, then clusters. Complexity accumulated, layer by layer. Nothing was skipped. Nothing was rushed. This gradual assembly explains why galaxies show such diversity. Each one carries a unique merger history, a unique path through the cosmic web. Some grew quietly, accreting gas and forming stars steadily. Others were shaped by violent mergers, their disks destroyed. Their stars scrambled into spheroids. Some were stripped, starved, or quenched by environment. These differences are not random. They are the natural outcome of hierarchical growth. And crucially, dark matter ensures that this hierarchy is preserved. It prevents early structures from being erased by later ones. Small halos do not vanish without a trace. They are absorbed, stretched, and redistributed, but their influence persists. You can see this in stellar streams. Long, thin ribbons of stars left behind when small galaxies are torn apart by larger ones. These streams trace the gravitational field of the host halo, with exquisite sensitivity. They are the ghosts of past mergers, still moving along paths defined by dark matter long after their original homes are gone. This is another form of memory. Hierarchy also explains why the universe looks different at different epochs. Early on, galaxies are smaller, more chaotic, more gas-rich. Mergers are frequent. Star formation is intense. As time passes, halos grow larger and deeper. Gas heats. Cooling slows. Star formation declines. Structure becomes more settled. None of this requires fine-tuning. It emerges naturally from the properties of dark matter and gravity acting over time. And this is where an alternative universe reveals itself by contrast. If gravity alone were modified instead of supplemented by dark matter, structure formation would be fundamentally altered. You might fix galaxy rotation curves, but you would lose the correct timing. Small structures would not form early enough. Large structures would appear too late. The observed population of galaxies at high redshift, young, massive systems already in place, would be impossible to explain. The universe would look perpetually unfinished. But our universe is not unfinished. It is aged. It has layers. This layered construction is why cosmologists can read time into space. By mapping the distribution of galaxies across different distances, they are effectively looking at different moments in cosmic history. The web thickens, clusters grow, voids expand. The pattern evolves, but its logic remains intact. Dark matter is the thread that runs through this entire process. It links early fluctuations to late-time structure. It ensures continuity across billions of years. It makes the universe legible. There is a subtle philosophical consequence here. Hierarchical growth means the universe does not forget its mistakes. Early accidents are not erased, they are incorporated. A slightly denser region becomes a filament. A filament becomes a cluster. A cluster becomes a dominant feature of the cosmic landscape. Small differences compound. This is why the universe is both orderly and uneven. Why symmetry exists alongside extreme variation. Why patterns repeat without being identical. Dark matter amplifies difference without destroying coherence. And this brings us back, once again, to visibility. At every stage of this hierarchy, ordinary matter plays catch-up. It falls into structures that already exist. It cools where allowed. It forms stars where permitted. It lights up regions chosen long before photons had any say in the matter. Stars do not build the universe's timeline. They illuminate it. The most unsettling implication of all is this. If you removed every star, every galaxy, every atom capable of emitting light, the universe's structure would still exist. It would continue to grow. It would continue to merge. The hierarchy would proceed, silently, invisibly, according to the same rules. Light is optional. Gravity is not. By the time stars appear, the story is already well underway. Which means that what we usually call cosmic history is really just the visible fraction of a much deeper narrative. A narrative written in mass, motion, and time, long before anything learned how to shine. And once you see that, the final step becomes inevitable. If dark matter governs motion, stability, memory, placement, architecture, and growth, then its role is no longer that of a missing ingredient. It is the main character. The visible universe, the one we name, categorize, and admire, is a secondary phenomenon, a thin, luminous layer tracing the consequences of something far more dominant and far more indifferent. So the last question is not whether dark matter exists. The universe has answered that already, in too many ways to ignore. The question is whether we are prepared to accept what that answer really means. Because if dark matter has been quietly building the universe from the beginning, deciding what forms, where it forms, and how it survives, then the cosmos we see is not the universe itself, it is its shadow. And understanding that shadow may be the closest we ever come to understanding the invisible hand that shaped everything we know. By the time you reach this point, the pattern is impossible to ignore. Dark matter is not an accessory. It is not a correction term added to rescue theories. It is not a footnote lurking at the edge of cosmology. It is the quiet ruler of motion, the unseen authority that decides how matter moves, where it gathers, and what is allowed to endure. Every scale we have touched leads back to the same conclusion. Stars orbit as if embedded in something vast and invisible. Discs survive because something absorbs their chaos. Galaxies remember because something smooth preserves their motion. Mergers resolve because something collisionless mediates them. Stars ignite only where something deep enough permits gas to cool. Filaments stretch across the universe because something non-luminous collapsed first. Structure grows hierarchically because something patient laid foundations early and never let them go. And at no point did light ever take the lead. This forces a profound reframing of what we mean by a galaxy, by structure, by even the universe itself. What we see is not the main event. It is the visible consequence of something else doing the real work. Luminous matter does not define cosmic architecture. It decorates it. Dark matter governs motion with indifference. It does not care whether stars shine or fade, whether galaxies are blue with youth or red with age. It responds only to mass and gravity, and in doing so it enforces rules that light must obey. Those rules are strict. Orbits must remain bound. Disks must not overheat. Gas must not escape too easily, nor stagnate forever. Mergers must dissipate energy without destroying coherence. Structure must grow early enough to matter, but slowly enough to survive expansion. These are not aesthetic preferences. They are constraints imposed by physics, and dark matter is the medium through which they are applied. Seen this way, the universe begins to look less like a luminous tapestry and more like a shadow play. The bright patterns we admire are projections cast by an invisible framework. Remove the framework, and the patterns collapse into incoherence. Remove the light, and the framework remains. There is something unsettling in this realization, because it cuts against a deeply human instinct. We are visual creatures. We trust what shines. We name what we can see. For most of our history, light has been synonymous with existence. Darkness has meant absence. Cosmology tells us the opposite. Most of what exists does not shine. Most of what matters never announces itself. The dominant influence in the universe is something we cannot touch, cannot see, and may never interact with directly except through gravity. And yet, it is astonishingly reliable. Dark matter does not behave capriciously. It does not introduce chaos. It enforces order. It makes galaxies possible, not fragile. It allows complexity to persist instead of tearing itself apart. It creates a universe where structure can exist for billions of years without constant intervention. In that sense, dark matter is conservative. It preserves. It stabilizes. It remembers. This also explains why the search for its particle nature, while important, is almost beside the point from a cosmic perspective. Whatever dark matter is made of, whether it is one particle or many, whether it interacts weakly or not at all, it has already done its job. The universe we inhabit is its finished work. Stars, planets, chemistry, life, all of these are downstream effects. We often ask whether dark matter is mysterious. That depends on what we mean by mystery. Its identity may be unknown, but its behavior is anything but vague. It is one of the most empirically constrained components of reality we have ever inferred. Its fingerprints are everywhere, etched into motion, structure, and time. The mystery is not that it exists. The mystery is how easily we once assumed it didn't matter. And there is a final, humbling implication that lingers beneath all of this. If the universe is governed primarily by something invisible, something indifferent to light and life, then our place within it is both less central and more remarkable than we often imagine. Less central, because the cosmos was not built with us in mind. The rules that shaped it were written long before stars, long before planets, long before biology. Dark matter did not arrange itself so that life could emerge. Life emerged because it was allowed to, in rare pockets where invisible constraints happened to permit it. More remarkable, because within a universe dominated by darkness, complexity still found a way, light still ignited, consciousness still arose. Not because the universe favoured it, but because the structure imposed by dark matter made stable environments possible at all. We are not the purpose of the universe. We are the consequence of its stability. And that stability comes from something we cannot see. So when you look up at a spiral galaxy and admire its symmetry, or at a cluster blazing with hundreds of billions of stars, or at the cosmic web traced faintly across the sky, it is worth remembering what you are actually seeing. You are not seeing the universe's foundation. You are seeing its surface. The true architecture lies beneath, silent and unseen, guiding every orbit, every merger, every filament, every void. It does not glow. It does not speak. It does not care whether it is understood. It simply does what gravity demands. Dark matter is not hiding. It is not waiting to be revealed in some dramatic flash of discovery. It has been telling us what it does all along, through the calm persistence of galaxies that should not exist, through the ordered motion of stars that should have escaped, through a universe that behaves far too well to be held together by light alone. what it really does to galaxies and to everything else is this: it makes structure possible and then quietly steps back, letting the luminous universe take the credit. In the end, the deepest truth may be the simplest one. The universe is not ruled by what shines. It is ruled by what weighs. And everything we see is shaped by something we never will.